Hello, and thank you for watching the second instalment of the Institute of Knowledge in Research in Science, second instalment of particle physics. Today we shall be discussing quantum mechanics. For more detail on quantum mechanics, particle physics and other interesting areas within science, the sciences and all knowledges and mathematics, please Google tiokrs to find our website. So quantum mechanics is the look at the microscopic fundamental scale of all matter. Quantum mechanics can be broken up into three different groups. We have virtual particles, leptons, and quarks. Quarks are fundamental particles, which means they cannot be broken down into smaller particles. These particles form larger particles, which we know as protons and neutrons and other types of particles. So quarks, the particles that quarks form are known as hadrons. Hadrons can be divided into two groups, mesons and baryons. Baryons are particles that are formed of 3 quarks, whilst mesons are particles that are formed of 2 quarks, a quark and an antiquark. Popular, well-known particles such as proton and neutrons are known as baryons, as they are formed of 3 quarks. Yes, so mesons are formed of quark and an antiquark. Such mesons can be, I believe it was the pion, which is an up quark, and an anti-down quark. Quarks have properties such as charge. Yes, they have properties such as charge, and the charge in particle, in the quarks, the different quarks, attribute the properties of the end particle. So an up quark, I believe, has a charge of 2/3 plus positive 2/3, and a down quark has a charge of, I believe, minus 1/3. So you will realize that for 3 quarks to be made to create a proton, you would need 2 up quarks and a down quark, and that will be 2 times 2/3, which is 4/3, then plus the down quark, which will make it have a positive charge of 1. Thus, a proton is formed of 2 up quarks and a down quark. The neutron, however, is neutrally charged, and we know that as it is a baryon, it must have 3 quarks, a combination of up and down quarks. Since a down quark has minus 1/3 and an up quark has 2/3 charge, we will realize that to cancel out the charges, you need 2 down quarks and an up quark to create a neutron, which is neutrally charged. The next type of fundamental particles we'll discuss is leptons. Leptons are light fundamental particles. They are a family of 12, 3 main particles: the electron, tau, and the muon. They have the same charge, or negative charge, but they vary in mass. They are light relative to other particles. What can we say about them? They have a charge of -1, and they have their accompanying particles known as neutrinos, and all of these particles also have antiparticles. Neutrinos are, there's a high abundance of neutrinos in the universe, about 1,000 million times more than the protons and neutrons in the universe. Neutrons are thought to be either massless or very light. If neutrons do have mass, then it will explain what dark matter is, which dark matter is thought of to be, was thought that the universe hasn't got enough mass for the gravitational attraction that is measured in the universal measurements. So that will explain where the gravitational force around the universe has come from, if neutrinos do have mass. Large water tanks are used in experimenting to help look for neutrinos and different leptons that are coming in from the sun rays and solar weather coming from the sun, as such a large number comes to Earth. But these neutrinos are very unreactive. The next part of fundamental particles we shall look at are gauge bosons, which are virtual particles or exchange particles. These are particles that are used in the four fundamental forces that are exchanged between particles to give the that create the force the force that we understand. The four fundamental forces are the strong force, gravitational force, electromagnetic force, and the weak force. The gravitational and electromagnetic force have infinite scale but are fairly weak compared to the strong force, and the weak force is also quite strong but far weaker than the strong force. The strong force is very strong but has a very minute scale. It works within the nucleus and holds the protons and neutrons together in the nucleus. The weak force is responsible for decay in radioaction between it converts as a neutron is breaking down into a proton in beta minus decay. It converts one of the down quarks into an up quark, thus releasing an electron and an electron neutrino. So the virtual particle responsible in the weak interaction is known as the W particle, W minus particle, or the Z particle. These particles are exchanged between other particles as to result in a force that we understand as the weak force. The particle responsible for the strong interaction is the gluon. This is exchanged between a proton and a neutron to keep them within a near distance within the nucleus. Electromagnetic force is responsible for electricity, magnetism, and the forces that we understand and are aware of today, such as pulling a car along the road, or standing up, or falling over. Any of the forces that you can imagine, everyday forces that we experience, are due to the electromagnetic force. Electromagnetic force is to do with charges, electricity, and magnetism on the more fundamental scale. The virtual particle exchanged between the electromagnetic force is known as the photon. The next fundamental force is gravity. The exchange particle has not been discovered yet, but it has been theorized, and it is known as the graviton, the God particle, or the Higgs boson. Much work is being done at the Large Hadron Collider in order to find this particle. These four fundamental forces are all the fundamental causes of all the forces that are observable or known in the universe. Next, we shall be looking at spin. Fundamental particles, many different types of particles, also have what is known as spin. Particles with half spin are known as fermions, and particles with full integer spin are known as bosons. Baryons, such as proton and the neutron, are fermions, as they have half integer spins. Half integer meaning 0.5, 1.5, 2.5, and so on. Mesons, which are the hadrons, which have two quarks, a quark and an antiquark, are known as bosons, as they have a full integer spin, either 1, 2, or 3, and so on. So virtual particles are also known as bosons, as they have integer spin, whilst leptons are fermions, as they only have half integer spin. Next we shall discuss the conservation in experiments and changing of particles and forces, there's something known as conservation. Mass energy conservation can also be looked at in more detail as mass energy conservation. Also, what needs to be conserved in an experiment are the baryon number, the charge, and the lepton number, and also the spin. Such experiments where these observations are not conserved have not been observed, and we do not intend to observe them, as this will contradict the theory and understanding of what we know of in particle physics. Now, just more detail of neutrinos. Neutrinos were thought of, I believe, by Pauli to have existed as in radioactive decay, alpha decay conserves the mass energy, whilst beta decay did not conserve the mass energy. It was thought that the neutrino, which had not been discovered yet at the time, carried the remaining energy to conserve the mass energy within the beta decay. I believe his name is Cohen and Raines. Under 30 years after Pauli's suggestion, were looking for the antineutrino in beta plus decay, when a neutron breaks down into a proton, releasing an electron and an electron neutrino. They managed to find it and wrote back to Pauli very happy and excited of their discovery. That is the end of our discussion on quantum mechanics. Please, if you feel free, leave a comment, and please check the website by googling TIOKRS, Institute of Knowledge and Research in Science. Thank you. Have a nice day.